Hello guys. Good morning. Good morning to all of you. Once again, welcome. Welcome to another session. Before I start, let me know if everything is all right, so that we can start it in full speed. Okay, I hope everything is all right. So without any further ado, let's start today's session. So today we'll be discussing LS-JJ coupling and term symbol. This is the first part. Let's see how much we can cover today. Good morning, Harry. So before we start, let us get introduced with some terminology which will be used in the upcoming discussions. So these terminologies are very important for you to understand. We define some terminology associated with the atomic energy levels. First of all, what do you understand by state? State of an atom is the condition of motion of all electrons. Atom is consisted of electrons. So specifying state means specifying the condition of motion of all the electrons. How do you specify the condition of electrons? We specify the condition of electron by listing their quantum numbers. 4 quantum numbers we have: N, L, Ml and Ms. Okay. If several states have the same energy, they are said to be degenerate, otherwise non-degenerate. The state with lowest energy is the ground state energy. So remember, okay, it is about the electron. Now, what is energy level? Energy level is collection of such states. Okay? A collection of states having the same energy in the absence of external magnetic or electric field makes an energy level. So an energy level will be denoted by a quantum number, that is the total angular momentum. Level with lowest J is the ground state. Okay. Next, sublevel. What do you understand by sublevel? Sublevel, any energy level may get split into energy level into several sublevels, maybe by the influence of some external influence, each characterized by one or more magnetic quantum numbers, ml. So you got the idea of state, level and sublevel. Now term. What is term? A collection of levels. Energy levels we have. A collection of levels will be called as term. The collection of levels characterized by an orbital angular momentum and multiplicity. Comprises a spectroscopic term. For example, 3D term. So it has 3 J values. 3D term means the weighted average energy of 3D3, 3D2, 3D1. Here J value is 3, here J value is 2, here J value is 1. So we define a level by specifying its J value. The term is collection of these levels. We have multiple J values here. Okay. So we specify it by specifying the orbital angular momentum. There it is, let's say D. D is equals to L is equals to 2. Okay. S, P, T, 0, 1, 2. And multiplicity. The term here is called the multiplicity. Now let us talk about configuration. Good morning, Molly. What is configuration? The specification of quantum numbers N and L. So you must have heard about the term electron configuration. So what is that configuration? In the while writing the configuration, we specify the quantum numbers N and L. For the orbitals of all the electrons of an atom is called the electron configuration of the atom. For an example, if you consider the carbon atom, 1s2, 2s2, 2p2. So here we are specifying the N value and this will give you the L value. Here it is L equals to 0. Okay, here is L equals to 0, P, L is equals to, okay, N is equals to 1 here, N equals to 2 here, N equals to 2. And this cell, S subcell, holds 2 electrons. Here it holds 2 electrons, P subcell or holds 2 electrons. Okay. P you already know this. S can hold 2 electrons, one is up and one is down. This is because of the Pauli's exclusion principle. Maximum 2 electrons can be held in one box. For P, you see 1, 1, 1, then in this way it gets filled up. Okay, electrons will be filled up singly first, Auber principle is. Then they will make pair. If you have 2 P2, P2 means it will get filled in this way. 1. If there are 5, then 3, then pair will be formed. 4, 1 unpaired electron will be. Now equivalent electrons. So if you consider this, let's say S2 or P2 or P6, whatever you have, orbital with same N and L values. Now for an example, 2p2, 2p2 here it has 2 electrons, right? 2p2 has 2 electrons. 1 for this electron, L value is 1, N value is 2. For this electron also, L value is 1, N value is 2. So in this electrons, these electrons are called equivalent electrons. Okay, or orbital. These are called equivalent electrons. The orbitals are equivalent orbitals, which are same N and L. The electrons in the equivalent orbitals are called equivalent electrons. This term will be used later on also. So remember this. Statistical weight. Number of distinct states in a specified collection is called the statistical weight. So we have talked about level, which is correct, energy level, which is characterized by J. So for this, the statistical weight will be J plus 1. We have talked about terms, collection of energy level. So for the term, the statistical weight will be S plus 1, L plus, and if you consider a single method, you know it already. The statistical weight is E and S. Okay. So this is important. Now these are some terms which you need to keep in mind. Now spectral lines. Once you get energy levels, you can get now spectral lines. So various things are there, like component. What is component? A transition between two sublevel is called component. Between two sublevel is called component. Line, a transition between two levels is called line. Thus a line is a blend of components. Multiplet, a collection of transition between two terms are called multiplet. Multiplet consists of number of lines. Then what is resonance line? Lines with the lowest frequency. Line of lowest frequency is called the resonance line. Okay, so let's say if you have the ground state and you have the higher states, so which one will be the lowest frequency? Lowest frequency means energy gap is minimum, means obviously this one will be the resonance line. Okay. So buzzing sound in background is high. Hello. So buzzing. Just a moment. Is there any improvement in the sound quality, or is it the same? Harry? Tell me, is there any improvement? Okay, so let's start once again. Now, the first thing which we will be talking about is LS coupling. This is also known as Russell-Sanders coupling. You see, the angular momentum of the electrons L and S, they interact magnetically. We have talked about it already. You see, this is known as spin orbit coupling, the coupling between L and S. They exact torque on each other. These internal torques do not change the magnitude of the vector L and S, but cause them to precess uniformly around the resultant J. You can see S, this is precessing about J. L is also precessing about J, their resultant, because they are internally connected as they exact torque on each other. So if the atom is free, atom is in free space, so that no external torques act on it, total angular momentum J is conserved in magnitude and direction, and as a result, angle between L and S would remain invariant. Now, when we apply magnetic field, the things get changed. We have already talked about it in the last lecture. Okay. Now, before going into the spectroscopic symbol, let me just show you how different spins get combined. If you have 2 spins, if you have 3 spins, then how they get combined. So let us talk about that. This is, we are calling spin-spin correlation effect. Spin-spin correlation effect. Look, individual angular momentum coupled with one another. Individual spin angular momentum coupled with one another. How? Let's say if you have one electron. For one electron, the scenario is pretty simple. We have S is equals to half for one electron. So total S, capital S will be same, and as a result 2s plus 1 is equals to 2. So this is doublet. Okay. Now let's say we have 2 electrons. So one S will be half, another will also be half. Both are electrons, so both are spin half. So your capital S will have a value between S1 minus S2 to S1 plus S2. So you can see half minus half 0 to half plus half is 1. So what you get, 0 means 2s plus 1. So 2 into 0 plus 1 is 1, and 2 into 1 plus 1 is 2. So we 2 into 1 plus 1 is 3. So what you get singlet, and you get triplet, right? Now let's take the case of 3 electrons. So maximum you can have up to this. So 3 electrons means S1 will be half, S2 will be half, S3 will also be half. Then S will be, you can see here 3 things are there. So how many possible combinations you can may be there? Half. Okay. If you combine them, let's say up, down, up, down, up, or half, half, and 3/2 may also be there. Okay. So you get half, you get a doublet, and 2 into 3/2 plus 1, so 4, quadrat. Now in the same logic, coupling of individual L's, angular momentum coupling we can also see. Let's say we have 2 L values for 3p 3d, 1 electron. These are non-equivalent electron. You see, this for this electron from 3p, n is 3, L is 1. For this electron from 3d, n is 3 and L is 2. So they are non-equivalent electron. Okay. So for the first electron, L1 is equals to 1, and for the second electron, L2 is equals to 2. So your L value will be varying between L1 minus L2 to L1 plus L2. So this will be 1 minus 2 is minus 1. So 1, 2 and 3 corresponding to P, D, F states. Now if you have more than 2, let's say for 2p, 3p and 4d. So 2p, these are all non-equivalent electrons. L1, 2p, L1 is equals to 1, L2 is equals to 1 again, L3 is equals to 2 again. So here you can see the L values, possible L values are 1 plus 1 minus 2, so 0, and 1 plus 1 plus 2, 4. So in between all the values will be allowed, 1, 2, 0, 1, 2, 3, 3, 4. Okay. In this way you make the couplings. So most of the time you are given this combination of 2 electrons, equivalent or non-equivalent. Let us now talk about the spectroscopic term symbol. Look, generally atomic states are described by this term symbol. You see 2s plus 1, this is the multiplicity term Lj. Okay. Now this is not always used, but most of the time it is used. It's the total spin quantum number, total, you see, total spin quantum number. 2s plus 1 is known as the spin multiplicity, which represents the number of possible states of J for a given L and S. Look, this formula will be used when L greater than or equal to S, and most of the time this condition holds. L greater equals to S, then you will write 2s plus 1. If L less than S, then the maximum number of possible J will be 12 plus 1. Then this spectroscopic symbol will be written in this way, 12 plus 1 Lj. Instead of writing 2s plus 1 Lj, we will be writing 12 plus 1 Lj. But this is not generally shown. Most of the time, when you talk about the spectroscopic term symbol, this is used, because most of the time L is greater than or equals to S. Okay. Now the L is total orbital quantum number. For corresponding value of 0, 1, 2, 3, 4, 5, we call them S, P, D. No, there is no E. S, P, D, F, G, H. No E. Remember this one. S, P, D, F, G, H, and so on. Now let us try to write spectroscopic terms for different symbol. In this regard, let me just tell you the very fine difference between the two terms. There are two terms and you already know it. How do you represent a level and how do you represent a term? We have already talked about it. When you talk about level, we have to write this in this way, 2s plus 1 L, this is level. And when we write term, we do not mention the j value. Okay, we write only 2s plus 1 L. Okay, this is a basic difference between level and term. Level has a particular j value. Term is combination of j values. So j value is not mentioned in case of term. Now spectroscopic terms for equivalent electrons. Equivalent electrons means you know it. What are the equivalent electrons? S2, P6, all are equivalent electrons. So if you have a closed cell, S2, here the 2 electrons of s orbital are equivalent. P6, p orbital, 6 electrons, they are equivalent. D10, maximum it can hold 10 electrons, or F, it can hold maximum 14 electrons. So if you have closed cells, they always form one S0 term. Okay. Now, if you consider, let's say, a structure like this. You see, if you want to write term of P1, P1 means this is equals to term of P5. You see here only one word electron, 1, 2, 3, 4, 5. So these two are equivalent. This is for P1, this is for P5. So these two are equivalent. In a similar fashion, if you want to write term of, let's say, D2, term of D2 will be equals to term of D8. Okay, because you know in D2 we have like this 1, 2, 3, 5. This is D2, sorry, D orbital. So if you write D2, D2 means 1, 2, D8, 1, 2, 3, 4, 5, 6, 7, 8. So you can see they are equivalent. I hope this is clear. So let us try to calculate this term for D2. For example, we are calculating the spectroscopic terms for D2. D2 means there are 2 electrons. 2 electrons we have. One is this electron, another one is this electron. For the first electron, you can see what is the value of S1. They are electrons, so spin half. Another electron S2, spin half. Now how will they get combined? S1 minus S2, S1 plus S2. So this will give you the value of 0 and 1. Now L1, sorry, ln y ln h half. D2. So for this electron L1 is equals to SPD 012. For this electron also same because their electron, their n and l values will be same. Okay. So what will be L? L1 minus L2 to L1 plus L2. So 0, 1, 2, 3, 4. Now for equivalent electrons there are some rules. Okay. So the rule is as follows. Remember this rule while we tackle the equivalent electrons. Rule for equivalent electrons. Number 1, even S will combine with even L. Okay. Even S will combine with even L and vice versa. Odd S will combine with odd L. And remember 0 always taken to be even. You may get confusion about 0. So 0 you will consider even. So you see, if I consider these combinations, so 0 will combine with 0, 0 will combine with 2, 0 will combine with 4, right? So this will be used to calculate the value of J, because ultimately we require 2s plus 1 Lj. So S values we have got. So S is equals to 0 will combine with L is equals to 0, L is equals to 2, L is equals to 4. S equals to 0, L equals to 0, so J is equals to 0. So what will be the corresponding term? 2s plus 1, so 2 into 0 plus 1 is 1, then L equals to 0 is S and J is 0, 1 is 0. Now if you consider S equals to 0, L equals to 2, what will be the value of J? J will be 2. So 1 D 2, L equals to 2 means D. Here J is equals to 4. So 1 4 S P D F G. So 1 G, J equals to 4. Get it? Now odd S will combine with odd L. So S is equals to 1. S is equals to 1 will combine with L is equals to 1, L is equals to 3. These 3 combination will be there. So if S is equals to 1 combines with L equals to 1, what will be the value of J? The value of J will be between L minus S to L plus S. Previously it was 0, so there is no issue like this. So 0, 1 and 2. And correspondingly the terms will be 2s plus 1 is 3, L equals to 1 means P. How many J values? 0, 1, 2. So the term you can write 3P. Okay, it has 3 J values. Here what will be the value of J? Again L minus S to L plus S. You see 3 minus 1 or 1 minus 3 minus 2, so modulus, so 2. It will start from 2. Maximum is L plus is 4. So 2, 3, 4. What will be the terms? Again 3, L equals to 3, S P D F, so F 2, 3, 4. So this will also be the term of D8. Clear? बताइए दोस्तों. So these are the spectroscopic term. One is 0, 1d2, 1g4, 3p0, 3p1, 3p2, and 3f2, 3f3, 3f4. So this even combines with even, odd combines with odd. This applies for equivalent electron. Remember, equivalent electrons, these kind of electrons. Do this problem. The ground state electron configuration of 22 titanium is argon 3d2 4s2. Which state in the standard spectroscopic notation is not possible in this configuration? Karthik, I don't understand the meaning of equivalent electrons here. Equivalent electrons, let's say if I consider D2, okay. So here 2 electrons are coming from D, so they are equivalent. Now let's say one electron is from 3D, another electron is from 4D. Although they are from D orbital, but one is from 3D, another is from 4D, so they are non-equivalent. Okay, let's say 3D2. Understood? Non-equivalent. Term doesn't contain J, but you wrote it, sir. Yeah, in general, we are calling spectroscopic terms. Okay. Yeah. While strictly speaking, when you call term, then this J value is not necessary. Okay. Here, because the J value is not varying, so you can write one is term, one is 0 term. It doesn't make so much difference. Okay, you know it. For all of them, J value will be 0. Do it. In this question, it is non-equivalent. How non-equivalent? What is the outermost electron? You have to consider this one. 4s2, 3d2. This one, right? So it is talking about D2. For S2 it is closed cell. So 3D2 obviously the outermost cell. So you have to consider the spectroscopic terms for D2. So, out of this state, which state does not belong to this D2? So, we can say it from the previous calculation only. Na? We have already calculated for D2. We have 1 S0, 1 D2, 1 G4, 3P0, 1 2, 3F 2, 3 4. So, 1 S0 was there, 1 D2 was also there, 3P0 was also there. So, 1F3 was not there, right? So, option A. Yes. Okay, let us calculate for the equivalent electron of P3. If we calculate for P3, what kind of results we can get? Do it, everyone. P3. So, here it is 3 electrons from the p orbital. So, this is equivalent electron. Okay? 3 electrons from the same p orbital. So, S1 is equals to half. Currently, we are discussing about equivalent. S2, S3, all of them are half. So, correspondingly, we will get the value of S to be half, half, P by 2. L1, 1, L2, again 1, L3, again 1. We will get the L values 0, 1, 2, 3. Okay. So, there is no even odd situation here. So, S is equals to half will combine with L is equals to, let us say, 1. This is a very special case. Okay. So, J will be your half and 3 by 2, and correspondingly we will get the terms 2 P, spectroscopic term 2P, and the J values are half 3 by 2. S is equals to half, L is equals to, let us say, 2, J will be equals to 3 by 2, 5 by 2. We will get 2D P by 2, 5 by 2. S is equals to, let us say, 3 by 2, L is equals to 0, J is equals to 3 by 2. We will get 4 S 3 by 2. So, only these terms will get, other terms get vanished. This is an exception. Okay. Okay, so once the equivalent electrons are done, let us go for non-equivalent electrons. Non-equivalent electrons. Number 1, atoms with only one optical electron. For an example, for hydrogen atom. 1s. So here S is equals to half. Okay, L is equals to 0. So as a result, capital S will also be half, capital L will be 0, and J will be half. So term symbol, spectroscopic term symbol will be 2s plus 1 L. When we only talk about term, we will write 2s plus 1. But when you are writing about term symbol, then this is a complete specification, 2s plus 1 L. Okay. So this is equals to 2s. Atoms with 2 or more non-equivalent optical electrons. For an example, 4p, one electron from 4p, another electron from 4d. For the above cases like that, that is an exception, okay, for because that is half filled subcell. So some things happen there. P3, if you consider P3, so it is half filled subcell. So because of that, few terms get vanished. Look, 4p, 4d, for the first electron, S1 is half, for the second electron, again half. So we will get S values 0, 1. Now here there is no restriction like even S will combine with even L and odd S will combine with odd L. There is no such restriction here. L1 for P it is 1, L2 for D it is 2. So you get the value of L to be 1 minus 2, 1 plus 2. So it is 1, 2, 3. So here S is equals to 0 can combine with L is equals to 1. It can combine with L equals to 2. It can get combined with L equals to 3. And correspondingly they can give you J equals to 1, J equals to 2, J equals to 3. And you get the terms 1 P1, here SPD 0, 1, 2, 1 D2, here you get 1 F3. Okay. S equals to 1 can get combined with L is equals to 1, L is equals to 2, L is equals to 3. So J is equals to, you see, 0, 1, 2. So it is 3p terms. 3p term, or you can also write it in this way, 3p term symbol, 3p 0, 1, 2. Okay, J is equals to 1, 2, 3. You can write these are 3D terms. Equivalently, it contains 3D 1, 3D 2, 3D 3. J 2, 3, 4. It contains 3 F, 3F terms. 3F term contains these 3 F2, 3, 4. Okay. Now the third possible case may be terms for 3 non-equivalent electrons. Actually, this is the second part of the second case. Let's say we have 3d, 4s, 4p. So they are non-equivalent electrons with s1 is equals to half, s2 is equals to half, s3 is equals to half. So for spin part there is no problem, every time it is half, and accordingly you get s is equals to half, half, 3 by 2. For L1 is equals to this 3 case is generally doesn't come in the examination, so you don't need to worry about it. We're just doing it for the sake of completeness. So 2s plus 1, 2s plus 1 is 2, 2 and L1, L2, L3, L3 is equals to 1 if you take. So 2p we can get half, we can get 3 by 2, and this will appear twice. 2d, 3 by 2, 5 by 2 will appear twice. 2f, 5 by 2, 7 by 2, this will appear twice because half is appearing twice. 4 by taking this 2s plus 1 is 4, 4p can give you half, 3 by 2, 5 by 2, 4d half, 3 by 2, 5 by 2, 7 by 2, and 4f, 3 by 2, 5 by 2, 7 by 2, 9 by 2. Mostly you can consider it in this way. From the values of s1, s2 and s3, we have to find the minimum value possible by combining it and the maximum value possible combining it, and the values in between are allowed with an interval of 1, let's say. In that way you can consider. So either you take s1 minus s2 plus s3, or s1 minus s2 plus s3. In that way you will get half, and when you add all of them you get 3 by 2. Now there is an interesting thing. You see, if you have noticed what we are actually doing, we are considering the s values for each electron, then we are combining it, okay, then we are combining coupling L and S by getting j values. So what is actually happening? Let us try to understand it with an example of 4p 4d. 4p 4d, let's say we have a level like this, 4p 4d. Four P 4d. This is unperturbed levels. Non-electron, non-equivalent electron. Now we incorporate spin-spin correlation. Spin-spin correlation. Spin-spin correlation, with the help of that, we can divide it into two things. one will be your S is equals to 0, another one is S equals to 1. So 4p 4d means we have considered this one, S is equals to 0, S is equals to 1. Okay. Then from S is equals to 0, you get L is equals to 1 to 3. So J is equals to 1 to 3. You get 1. What are the terms? What are the terms? Terms are 1p, 1d, 1f. These are the terms, right? 1p, 1d, 1f. So S is equals to 0, we are getting 1p, 1d, 1f. So 3 terms you see 1p, 1d, 1f. For S is equals to 1, we get 3p, 3d, 3f. This was the spin-spin correlation. And what is this? This is called the residual electrostatic. Because of this, it is getting divided 1p, 1d, 1f, and S equals to 1, 3p, 3d, 3f. And further it gets splitted by spin orbit magnetic energy, LS coupling. Okay. So from here you will get this one. From this you get 3 things. 1, 2, 3. Here also you get 3 things. So you get 1p1, you get 1d2, you get 1f3. Here what you get? You get 3p2, okay, 3p1 and 3p0. Here you get 3d3, 3d2, 3d1, and finally you get 3f4, 3f3 and 3f2. These things you get because of the spin orbit magnetic energy. Now try to solve this problem. In the LS coupling scheme, the terms arising from two non-equivalent electrons, p electrons. So two non-equivalent electron may be 2p, 3p or 3p, 4p, like that. So, you see all the terms are given. Can you do it? It is PP configuration, not P2. Here we are given P configuration. If it were equivalent electron, it would have been P2, but as it is non-equivalent, it is PP. What is the answer you are getting? Two P's are there. S1 is equals to half, S2 is equals to again half, and this gives you capital S 0 and 1. L1 is equals to P means 1, L2 again 1. So L 0 1 2. Now there is no restriction on combining even S with even L, odd S with odd L. So you can combine S equals to 0 with L is equals to 0, L is equals to 1, L is equals to 2 as well. This gives you J is equals to 0, J equals to 1, J equals to 2. And as a result, we get the term symbol one S 0. Here it is 1 P 1. Here it is 1 D 2. Now, if I want to write the term, we can write it in this way: 1s. Here it is, the term is 1p. Here we will write 1t. Okay. Now let's go for S is equals to 1. Could you find the answer, guys? Let me know the answer quickly. L is equals to 0, L is equals to 1, L is equals to 2. This gives you J is equals to 0, sorry, J equals to 1. This gives you J is equals to 0, 1, 2. This gives you J is equals to 1, 2, 3. And this gives you the term 2s plus 1 is 3. So 3s1, this gives you 3p012. This gives you 3d123, and correspondingly we will get the terms 3s, 3p and 3d. Advantage you are getting option D. 1s, 1s, 3s, 3s, 1p, 3p, 1d, 3d. Everything is there, 6 term. Option D. Clear, everyone? Or is there any confusion? This particular topic, spectroscopic term symbol, is very simple. In your examination, if you see any question, okay, you will answer, okay, my 5 marks is reserved, because from this particular topic atomic molecular questions will always come in part C. Okay, atomic molecular question, whatever question you get, whether easy, difficult, whatever question you get, it will give you 5 marks. That is why it is very important. Now let us talk about a very important thing, Hund's rule. Order of terms, rules given by Hund. Now you are getting terms. Now which term is the ground state term? That you need to understand. So order of terms, rules given by Hund. So if you just understand this simple thing, 2s plus 1 Lg. This thing is called spin multiplicity, right? Or in general multiplicity, right? So order of terms, to decide that, we'll consider from head to tail. 2s plus 1, you can say head, this is the body and this is the tail. J is tail. Head, tail, head, body, tail. Okay, so we'll start with this head. The first rule says that terms with largest multiplicity, if it is large, it is low. Terms with largest multiplicity lies lowest. Okay, so if this value, head value, is maximum, that term will be lowest. Now it may be possible that all the multiplicities are equal. Then if this is equal, you will come to L. Okay, so of the terms with given multiplicity, means multiplicity are same, that with, again, large means low, largest L lies lowest. Okay, now it may be possible that both of these terms are equal, multiplicity is equal, L values are equal, and let's say then you will come to J values. Okay, now for this J value, if you want to come, there may be 2-3 possible cases. You know, if you consider P2, let's say P2, so this is less than half filled, P3 is half filled, P4 more than half filled. So these scenarios may be possible. So in multiplets of equivalent electrons, in less than half filled, like P2 or D3, less than half filled subcell, what will be there for less than half filled subcell? Normal order, the level with lowest J lies lowest. You see, lowest J lying lowest, so this is normal order. Normal, lowest, low, lowest, low, normal order. Now if it is more than half filled, then reverse order, inverted order applies. Fourth, for more than half filled, maybe D4 or P4, maybe D6, let's say, that is more than half filled, or P4 more than half filled, subcell level with highest j lies lowest. You see, highest lowest. So this is inverted order. Yeah. Now it is less than half filled, more than half filled. So what remains? Half filled. So terms arising from half filled subcells, so only very slight fine structure splitting. And you know, from half filled subcell, all the terms will be S terms. We have already told you. The lowest term arising from half filled subcell are S terms and are stable. Now let us take some example to understand it better. So the main thing is you have to start with head and you have to find whether it is largest. If it is largest, means lowest. Then if the head is same, you will come to body. If body is same, you will come to tail. Let's take few examples. First example, carbon. You know the electron configuration of carbon: 1s2, 2s2, 2p2. So here you have to consider the p2, this one, p2. How p2 looks like? 1, 2. So this is, you can say that it is less than half filled. And what terms you get from p2? How many terms you get? If I write the terms 2s plus 1 lj, in terms of this, if you write, you get these terms: 1s0, 1d2, 3p0, 3p1, 3p2. Let's say you get these terms. Now as per Hund's rule, what you gonna write? Which terms are lowest? Terms with largest multiplicity. Here you can see 3p0, 3p1, 3p2. So they will come first. Now their spin multiplicity is same, p values are same. So what will be decided? It will be decided by j values, and from the j values you have to use this less than half filled, means level with lowest j will lie lowest. So out of these three levels, 3p0, 3p1, 3p2, level with lowest j will lie low. So which one is low? 3p0 is the lowest, 3p0 will be the lowest, and after that 3p1 will come, after that 3p2 will come. Next highest multiplicity is 1. Now we have two options, 1 is 0 and 1d2. So obviously here L value is more, so 1d2 will come, then finally 1s0 will come. Yeah. So here the ground state term is 3p0. Let's consider oxygen, 8O. So we have 1s2, 2p2, 2p4. Here we have P4, right? P4, 1, 2, 3, 4. We can say this is more than half filled. Okay, so let us first write the labels. We have 2s plus 1 L J. You can get these labels. 1 is 0, 1D2, 3P2, 3P1, 3P, 3P0, 3P1, 3P2. Look, same terms we will be getting because P2 and P4, they are equivalent, right? So same levels we will get. Now if I write it as per the Hund's rule, because of it is more than half filled, how will it get changed? First, what will be the first term? Tell me. We have 3P0, 3P1, 3P2. More than half filled means inverted order. Highest J will lie lowest. So here 3P2 will come first. 3P2 will be lying lowest, then 3P1, then 3P0. 1D2. Other things will be same. 1D2, more L value, lie lowest. 1 is 0. Is it clear, guys? Tell me. One third case, nitrogen. 1 is 2, 2P2, 2P3, P3, half filled. If we write the levels, 2s plus 1 Lj, 2p, 1d, 4s. Let's ignore this j. 2p, 1d and 4s. So 4s, 2d, 2p. Is there any question from this? Tell me quickly. Okay, this one is 2d, na? So let's solve this question. This came in GATE 2023. Atomic number of an atom is 6. What is the spectroscopic notation of its ground state according to Hund's rule? Simple question, do it. Spectroscopic notation you have to find out. Ground state, the lowest one. You have seen just now carbon atom, option A, yes, 3p0. Yes, C for carbon, option C, sorry, option A. चलो आगे बढ़ते हैं फिर. This came in June 2015. Of the following term symbols of NP2 atomic configuration, which is the ground state? अच्छा, we have already solved these problems ना. Three P zero ना. NP2 less than half filled. 3p0. Look, this kind of question, once you understand, even without doing, firstly you have to look for largest multiplicity. So 3, 3, 3. Okay. Out of that, this is normal order, less than half filled. Obviously 3p0. So look, you can find it in few seconds. You get questions like this. Do this one. The electron configuration of neutral manganese atoms is this, the ground state for Mn3 plus. Look, this one is a little bit Mn3 plus. 3 electrons, so 2 electron from 4s, 1 electron from 3d. So we get the configuration of Mn3 plus as argon 3d4. Look, let me share with you a short trick to calculate the ground state. Okay, if you are not interested in evaluating all the terms, you can just go for ground state term symbol. if you just want to calculate the ground state term symbol, you can follow this procedure. So you may have, let's say I'm taking example of the with the p subcell, p orbital. Let's say we have the electrons filled up in this way. So each electron will have their ml values and ms values, right? So ml and ms, so it is p orbital. So L is equals to ml values may be +1, 0, -1, and ms is plus minus half every time. So what you gonna do to calculate the ground state? You'll first, we need value of s na to write 2s plus 1. We need 2s plus 1 L j. Now we need s value. S you can calculate from sum of s, ms. So here you can see 2 up, so half plus half is 1. L value we can calculate by making this sum over ml. Now you need to decide j. J values, now there may be two cases, it may be more than half filled or less than half filled, and for half filled it is one is, you know it. So if less than half filled, if you are given such an electron configuration which is less than half filled, then you will choose the value of j to be L minus S. And if it is more than half filled, then you will choose the value of j to be L plus S. Actually this is a special case of the this is derived from the Hund's rule itself, okay. And if it is half filled, if it is half filled, then you can see the L values will be 0 na, ml plus 1 0 minus 1. If it is d orbital, it will be plus 2 plus 1 0 minus 1 minus 2. So if it is half filled, this L value sum over ml will be 0. So for half filled, j is equals to L plus S, L is equals to 0, so j will be equals to S. As simple as that. So here a D4 is given, okay. So for a D4, what we have, so you can imagine it in this way. So you can evaluate it by using Hund's rule. There is that way also, okay. So you will write ml and ms. ml is plus 2 plus 1 0 minus 1 minus 2. D4 1 2 3 4. So what is the value of L and what is the value of S? ms, each value is half, right? So what is S? Sum over ms. Half, how many times? 4 times. So 2. L, sum over ml. You see, plus 2 plus 3, 3 minus 1, 2. And here 2s plus 1 is equals to 2 into 2 plus 1, 5. It is less than half filled, right? Less than half filled. If it is less than half filled, so what will be the j value? J will be L minus S. Two minus 2 is 0. So the ground state term, what it becomes? 5. L is equals to 2 means D, j equals to 0, 5D. 0. Did you understand this? Now the same thing you can do using, let's say, Hund's rule. Using Hund's rule, you see, we have D4, right? We have this D4. So L we can get 2, S we can get 2. We have calculated it. So what will be the possible J values? J values will be L minus S to L plus S. 0, 1, 2, 3, 4. And the corresponding term symbols, levels will be 2s plus 1, 5, 5, D, 0, 1, 2, 3, 4. So if you write it, because this is less than half filled, we can write 5D0, 5D1, 5D2, 5D3, 5D4. Which one is lowest? 5D0. This is the ground state. So this is actually this thing. Will you be now able to calculate? So for P3, if you want to calculate, let's say for P3. For P3, let's calculate the ground state term for P3. ML, MS plus 1, 0, minus 1. P3, 3 electrons, 1, 2, 3. So L sum over ML minus 1, 0, minus 1. Okay, na? Plus 1, 0, minus 1. So this is 0. What about S? Sum over MS. Half, half, half. 3 by 2. And you know, for half filled, J is equals to S. 3 by 2. So ground state 2s plus 1, 2s plus 1, 4. So ground state will be 4. L is equals to 0 means S. J equals to 3 by 2. Clear? 4 is 3 by 2. Why don't we take 3 electrons from 3 term only for Mn3? Actually, it depends upon the energy, right? Which is favorable to lose energy. Which electrons are more favorable to lose? Here, we can easily remove 4s electrons. The 2 4s electron can be removed first. So there are few rules. Okay, I will share those rules. I think it is there in quantum mechanics or somewhere else. Depending on the value of N and L, the energies are decided. Based on that, we removed 2 electrons from 4s first, then we go for D electrons. Okay, if I get that, I will share in the group. Okay, I have to look for it. then I will set the rules. One problem I'm giving you as homework, take this problem as homework. How much does the total angular momentum quantum number J change in transition of chromium 3d6 atom as it ionizes to Cr2 3d4? Okay, so you will do this at home. Simple question. You will try at home. We can discuss this in the tomorrow's class. So if you have any question, you can ask. Otherwise, we can wrap up the session here. Thank you guys. Thank you very much for joining the session. Tomorrow we'll be considering JJ coupling. LS coupling is done today and spectroscopic symbol. JJ coupling, we'll talk about that JJ coupling a little bit, then it will be over. Thank you. Thank you very much. Bye bye. Take care. Have a great day. And everybody like the video. Okay, आप लोग like नहीं करते.